Okay, hi, and welcome to a video on our Calculus Chapter 4 notes, specifically Section 4.1. This will be the first of probably two videos for Section 4.1. We're going to be talking today about maximum and minimum values. You may follow along on notes if you receive them from your instructor. You can follow along just on your own paper and take notes on your own, whatever feels more comfortable to you, just so you understand the concepts when you're done and are ready to tackle that homework. So first thing that's important to note is that when we are talking about maximum and minimum values, for the most part, we are talking about on closed intervals. Okay, and so by that I mean if we look, we have a starting point, let's say x equals a, and a finishing point, let's say x equals b. And so oftentimes that closed interval will look like from a to b. And within that closed interval, there's two kinds of maximum and minimums that we will study. The first kind being what we will call critical numbers or turning points in some cases. The critical numbers are going to have a couple definitions, but I can see them here. So for example, if I label this point, probably right here, and actually probably this other end point up here. All of those points have something in common. If I draw the tangent line to the curve at that point, and forgive my lines if they're not perfect here, all of these tangent lines, that one's not great, but all of those tangent lines at those points are horizontal. In other words, where the tangent line is horizontal, or when the first derivative, where the first derivative is 0, I have what's called a critical number. Okay, so we can solve that using calculus, but let's define these points in terms of maximum or minimum. So as I read a graph, I read it left to right, just like I'm reading a book. So let's talk about this point where my cursor is here. I go down or decrease to the point, and after the point, I increase. And so by definition, we will decrease to a minimum and increase to a maximum. And these are specific maximums and minimums. These are what we will call relative or local maxes or mins. So I'll call this one a minimum. This one, I will just use the term local. So I will call this a local max. And this one, I will call a local min. And this I will call a local, or you can call them relative max. Okay, so those are what we are going to find first, are these sort of turning points, if you will, within the curve, because actually calculus can help us do that. Now, just based on location alone, I can't necessarily tell whether a point is going to be a minimum or maximum. So for example, yes, we know that we increase to that maximum and then we decrease after. And so I can see that that point right there that I just highlighted is a local maximum. But it just so happens to be above, if you look at its y value, if it were on a Cartesian plane, both of these relative or local minimums. But it doesn't have to be. So let me show you some common, maybe misinterpreted functions. So here's one. I'll just draw a vertical asymptote. So it's a discontinuous function. And on one side, maybe it looks like so, and on the other side, maybe it looks like so. Okay, and I'm not really too concerned with values. I can make them up as we get close, but you can kind of see what I'm going to talk about here in a second. So this point right here is going to be a local minimum. And that is by definition because we decrease to a min and we increase after. And this point down here is what we would call a local maximum because, again, we increase to it and decrease after. But if we really look at this y value is negative. This y value is certainly positive just based on where it is in my Cartesian plane. And so we can see that our max is actually below, in this case, our min. And that's because they are local or relative maximums or minimums. They are not necessarily determining where our y value is. They are saying that we have a turning point on our curve at that point, and it describes the behavior of your curve surrounding that point right before it and right after it. And calculus can help us find those. So that's why these sort of critical numbers become really important here. Where the tangent line is horizontal, which we just kind of talked about, that is a critical number. So that will help me find some of those turning points that we see on a graph. But any critical number, or to find a critical number, there's actually two parts of this definition, and the second one is the one that gets forgotten the most. And I'm going to add in here any new restrictions to the domain of f prime, or you could write in words the derivative, okay? So what that means is I need to kind of use some algebra here paired with my calculus knowledge. I need to look at the domain of the original function. Then I need to look at the domain of the derivative that I find. And I need to see if there's any new restrictions with that derivative. And what that usually means is there's going to be something interesting happening at that point. Maybe it's a sharp turn, maybe it's a kink or a cusp or something that looks like some of these that I've drawn up there. Okay? It's a point of interest that we're going to need to study throughout this chapter regardless. So before I continue on, I will just say that we are going to come back to that graph and we are going to look at how do we find an absolute max or min, but that's going to be on the next video. This video is just going to be about these relative or local max or mins and just identifying where these critical numbers are going to be. A critical number is therefore going to be the x value only. It's not going to be the y value. And so let's take a look at one of these that are already completed for us and see if we can't figure out what we're doing here. So the directions are find any critical numbers of the following functions. So the way the function is written right here might tell me that I need to use product rule, but as you can see, I went through a quick algebraic rewrite, and I do always write when I'm going to rewrite my function for multiple reasons. We've already kind of gone through that throughout this course, but if there is an error in something, I can go back to the rewrite and say, did I make a mistake early on? Are those two functions equivalent, etc.? But just makes me know that I haven't done any calculus yet. I'm just trying to rewrite it so I can do calculus or so I can understand it in a better way. So it doesn't matter to me whether you do the derivative, or excuse me, the domain from here or here, but the domain of the original needs to be discussed. And so it's just a polynomial curve. And so that has all reals as its domain or no restrictions, so negative infinity to infinity. You might also see that, which means all reals. You could also just write to yourself, no restriction. That would be fine too. And then once you find the derivative, before you set it equal to 0 and solve it, my suggestion is to find the domain. And that suggestion is because once you solve your equation and set it equal to 0 and you get your answers, you're very likely to just be done with the problem and not remember or look back at that second part of that definition, which dealt with the domain. So as soon as I find that derivative, I find its domain. And so if I look, it's still a polynomial curve. Now it's a third degree polynomial, but I still have no restrictions, or I still have all reals as my domain. So there are no new restrictions to my domain. There isn't anything that my derivative would exclude that is included in my original. Remember, a derivative describes the original, so you want your derivative only to exist where your original exists, but you also want to take a look at places where your derivative does not exist, but your original does. So, for example, my original exists at x equals 2, but for whatever reason my derivative does not. I need to look at that because then I don't have a good description for what my function's doing at 2, because that's what the derivative is going to do for us. Remember, it's sort of like an adjective describing the original function's behavior. So I have no new restrictions. So once I set my derivative equal to 0, here are my three solutions, 0, square root of 2, and negative square root of 2, and you would enter those as such. Don't write their decimals unless you were asked around, and that's it. So if we do one from start to finish, let's see what this looks like. So in this case, I am going to find the domain first, right? Because if you just start with your calculus, you might not ever look back at that second part of that definition, which does include domain. So I have 4x squared as part of it. I can certainly put anything I want into that place for x. It's just polynomial. And the same thing actually holds true for right there, okay? It's an exponential function. So x is in my exponent. I can put 0 in, 3 to the 0 is 1. I can put positive values in, 3 to any positive number just grows very quickly. And then negative numbers I can also put in because, for example, if x is negative 100, and I think about what is 3 to the negative 100, remember that just reciprocates. So what appeared to be repeated multiplication, like 3 to the positive 100, is just multiplying by 3 100 times. This now turns into repeated division because now I'm dividing by 3 100 times. It just becomes really, really small. It approaches 0. And if you remember the exponential growth model, this might be what 3 to the x as a graph looks like. And we do see a horizontal asymptote looking to the left, or as x approaches negative infinity, it does level off at y equals 0, but never crosses 0. So I have restrictions to my range, but no restrictions to domain. X can be anything. So again, I'll say negative infinity to infinity, or you can say all reals, whatever you're comfortable with. Okay, and then let's find the derivative, right? Because that's what we have to work with here. So I will find the derivative, y prime. So I'll use product rule. So the derivative of 4x squared, I'm just going to do this in the order that I see it. Derivative of 4x squared is 8x times the 3 to the x, and you can put this in parentheses if it makes you feel better. And then plus, leave the 4x squared alone. And now the derivative of 3 to the x would be 3 to the x times natural log of the base, or natural log of 3, technically, times the derivative of x, which is 1. All right, now it doesn't matter to me if you do a little bit of rewrite before you find your domain. We can't forget to compare it to this domain, right, of all reals here. If you do your rewrite, just be careful that you're not eliminating variables or dividing by certain things because you are potentially changing that domain. So I'm just going to leave it and just take a look at it. This part looks very similar to my original function in terms of, what I can do with x. X can be anything. That is the original part. I only now added that I'm multiplying by natural log of 3, which is some constant value. So my domain still is unchanged. It still is negative infinity to infinity. So I have no new restrictions. So I have no additional critical values from the domain. And I will show you one where we do, I promise. All right, so now if I set this equal to 0, I'm just going to rewrite this before I do anything. I do want to make an important note here. Well, I'm not going to write times 1. Other than that, I'm not going to do it. Okay, one important note is often people start dividing by different terms or factors or values or whatever when it still is y prime. And you definitely don't want to do that. So I set it equal to 0. Now I will go about my solving techniques that I learned from algebra. So for example, I'm going to factor out 3 to the x. Make sure you can read your own writing that it is 3 to the x and not 3x. I will also factor out, because see, I have 2 terms, really. Here's my first term. Here's my second term. So I could see easily they both had a 3 to the x. And then also they both have, let's see, 4x. And I'll just factor that out of each term. So that would leave me with just a 2 in the first term. And let's see, there'd be an x that's already factored out and natural log of 3. Now, don't panic about the natural log of 3. Natural log of 3, again, is just some value. So in here, it almost is like 2 plus 5x. I know natural log of 3 is not equal to 5. I'm just showing you that that's just some linear expression that I am not worried about at all. Okay, I know how to solve those. All right, so I now have 3 different factors. So your factor theorem says if it equals 0, go ahead and say the first factor equals 0. Second factor can equal 0, or this last factor equals 0. And then I will solve all of these. Well, 3 to the x, remember we looked at that graph a few minutes ago. It never crosses that x-axis. It never, ever goes through and has a y value of 0. You can also try taking the natural log of both sides. You cannot do the natural log of 0, so even if you were already here, natural log of 0 does not exist for this reason, right? Your exponential growth function does not cross that x-axis, so there's no solutions from that. 4x equals 0, I can divide both sides by 4, so there's one critical value. Then this is, remember, just a linear equation, so I will subtract 2, and I will divide by that coefficient. So I'll divide by natural log of 3. And again, don't give the decimal unless you were asked to round. If you're asked to round, then go ahead. Otherwise, these are your 2 critical values. Okay, now if I look back at both of these, one commonality in question A and question B here is that both domains were unrestricted from the beginning, and both of these were unrestricted when I did the derivative. So really not anything too exciting with their domains. So let's see once we get some domains in here. So C, same thing, right? Find critical values. So as I look through this, I might want to do a rewrite, and this is a personal decision or personal choice rather, as you are finding the domain, what you find easier. So this is x to the 1/2. So if I look at it like this, I'm going to distribute the x to the 1/2 in. When you're multiplying with the same base, you add your exponents. So that becomes x to the 3/2 minus 1 x to the 1/2. And I don't really need to write the 1, but I have it, so I'll leave it. So no matter how I look at it, I do need to be able to figure out the domain because it is restricted here. So anytime we see an even root, and I'm going to highlight how you can see your even roots, right? It's power over root. So all of these are square roots. And remember the index, unless otherwise written, is right there. So that's where all of those match. Okay, so in order to stay real, I cannot take the square root of a negative number. If we try to take square root of -4, it is 2i, I for imaginary. So I cannot do that to stay real. So we don't. However, if it's an odd root and I want cube root of -8, for example, It is -2 because -2 times -2 times -2, if you have three negatives when you're multiplying, your product turns out to be negative. So that's okay. So it depends on what your index is or what your root is, and that is found in the denominator, right, of your fractional exponents. So it doesn't matter to me how you see it. Now, I also need to think I can take the square root of 0. Square root of 0 is 0. So in this one, I would say include 0 to infinity because I can take the square root of very large positive numbers. The only numbers I cannot take the square root of are negative. You could also say it in such a way that makes sense to you using sort of like your number line thinking and just writing it as the inequality instead of the interval notation, and that would just be x is greater than or equal to 0. Make it make sense to you. So now that I have f and I have its domain, let's find f prime and we'll look at its domain. So it's power rule, right? That part should not be terrible at this point in the semester. All right, so I have my power rule derivative. And now let's pause and let's find domain. But again, anytime you do something algebraically, I really think turning your negative exponents into positive exponents might be something, it might be a good idea for you. Again, this is individual choice, but I'm going to do a rewrite of my f prime. And I'll be able to see it both ways, but I think some of you like working with square roots better. Some of you like working with the fractions better. You'll kind of get a feel for what you prefer. So 3 square root of x over 2 would be this first term. Minus, this is square root of x, but in the denominator. So I'll put that with the 2. And make sure you can tell as you look back at your problem, is your square root in the numerator or in the denominator? And that's why I put it with the 3, because sometimes you write 3 over 2 and you mean to write the square root of x times your fraction, but it ends up either too low or just in the wrong place, and I just wouldn't want misinterpretations to occur. So I think that's a good rewrite. Now if I look, and again, don't set it equal to 0 yet. If I look at it, I need to be able to determine domain. And again, it doesn't bother me whether you're from here or here, anywhere from that first derivative. Well, the x to the half, still being just square root of x, has the same restriction my original did, right? So far, I start with x has to be greater than or equal to 0, or 0 to infinity. That's what I'm starting with from that first term. But if I look at the second term, no highlighted here because this is an important one. If I look at the second term, that changes the game a little bit. If x is 0, because I'm saying I can include it, square root of 0 is 0. So my denominator becomes 2 times 0. And that's trouble because then that purple fraction there that I just highlighted becomes 1 over 0. So we should also remember a restriction to our domain that not only square roots, but denominators, right? So your denominator cannot be 0, whether it's a whole or a vertical asymptote. It's a point of discontinuity. So I can divide both sides by 2, and I can square both sides. X cannot be 0. So I can see it kind of one of two ways. Oh, look, x is in my denominator, right? Just as a factor on its own. So it cannot be 0. Or you can do the solving. So now that changes this to be a parenthesis because you cannot include it. And I'm going to try to delete the or equal to. It's just x is greater than 0. It is not x is greater than or equal to 0. So I do have a new restriction. And that new restriction is at 0. So this should be added to my answers of what are your critical numbers or critical values for this original function. This is an x value that I would want to do further investigation on when I'm looking at the behavior of my original function. Something happens to my curve at that point. That's all you have to know at this point in time. Is that's going to be a point of interest as we get to understanding these graphs a little bit more. That's what a critical value tells us. It tells us, where our function might have a turning point, a local max or min, or where does it have a sharp turn, a kink, a cusp, or things like that. Okay, so I have to add that one. And now let's go to our solving. I'm going to set my first derivative equal to 0. Okay. 3 rad x over 2 minus 1 over 2 rad x. And I'm going to go from a place where I think many of my students go from, which is the radicals. You are typically more comfortable solving with radicals than you are fractional exponents, but I can show you both because really they mean the same thing. So you can have similar techniques and you can get to the same answer either way. So when I only have two terms, I really like to add one to the other side. So I'm going to add this negative term to the left side. And then some of you learned this as multiplying both sides by the common denominator. Some of you learned this as cross multiplication. But again, this probably looks familiar to a lot of you, whether I agree with it or not, something different. But your technique is really common denominators. But this works. You have a proportion. So I can say 1 times 2 is 2. 2 times 3 is 6. But the square root of x times square root of x is a whole x. And so I can divide both sides by 6. Be careful, because it is, in fact, 1/3, not 3. That's another common error as we go through. Simple computational errors. That's if you wanted the radicals. Now, there's nothing wrong with solving these with their fractional exponents. So if that's your choice, I might first recommend multiplying everything through by 2, because when you do that, you eliminate at least your fractions in your coefficients, right? Because 0 times 2 is still 2. And then I want you to think about factoring. So when we factor, we typically, and go back to something like x squared minus 3x equals 0. Well, I'm going to factor out an x. Why? Because that is the smallest amount of x's I have, right? The smallest exponent is x to the first. So the smallest exponent I have here is x to the negative half. So that's an option. And then when I factor it out, I'm subtracting, right? So I subtract my exponents, 2 minus 1, because when you divide these powers, you subtract your exponents. So 1/2 minus negative 1/2 leaves me with a whole. In other words, and I'll put the 1 there just for a second, when you distribute this back in to check it, negative 1/2 plus 1 is positive 1/2. And then minus 1. And so I don't usually write that 1 because then it looks like a prime. And then my zero product property tells me I have x to the negative 1/2 is 0, or 3x minus 1 is 0. Here's my 1/3 answer. This one we need to be really careful. I'm going to highlight this. Do not be fooled by this statement. X to the negative 1/2 is 0. People like to automatically say, oh, good, so x is 0, because 0 to any exponent is 0. That is not true. 0 to the 0 is not 0, because we also said anything to the 0 is 1, right? So we need to be very cautious. And also, this is not repeated multiplication now. This negative exponent makes it repeated division. You can't repeatedly divide by 0. So if I just do one quick rewrite, we would see it, I think, right? That this is really 1 over x to the 1/2 equals 0. And I don't care again if you cross multiply or how you look at this, but in order to get a fraction to be 0, your numerator would have to be 0, and that can never be. So this has no solutions. So if you got your 0 from the incorrect solving here, that is not correct, right? But that is how some people get their 0, but it is not correct. It came from the new restriction. Okay, and then here's another one, right? And then I'll show you both again. So I'll do a rewrite of the original. So I'll write this as x to the 2/3 minus x to the 1/3, right? Power over root. And that may or may not help me. Again, you need to just be able to find your domain. Doesn't necessarily matter from which function. Okay, so I can tell that because I have a cubed root, right? I can see it here. I can also see it here, right? Power over root. There really are no restrictions to that domain because, again, I can have the cube root of -8. I can have the cube root of 0, etc. So there really aren't any restrictions here. So I'm working on -infinity to infinity. So now let's go to my derivative and see what happens there. So my f prime, again, this is why I like writing it as a power versus the radical. So I'll bring my exponent down, keep the base the same, subtract 1. And when you're subtracting 1, remember you're subtracting 3/3. Minus 1/3 x to the -2/3. There's my derivative. Again, oftentimes these derivatives aren't going to be the most difficult derivatives seen, but then maybe there's something about their domains that maybe we need to look at. So again, you can maybe go right from here to see your domain. I will tell you a big secret here that if your exponents go from positive to negative, you often will have a new restriction to that domain. Because if you look through your rewrite, this is 2 over 3x to the 1/3. Even if you write it as a radical or not, I still think you can see it from this view maybe a little bit better. And this is 1 over 3x to the 2/3. So now hopefully what you can see is that, sure, as far as the base goes, you can still put in a negative number here and take the cube root of a negative number. Same thing over here. I mean, I get that it turns positive because you're squaring it, but you can take the cube root of any number. That is still true. However, the new restriction comes because your denominators cannot be 0. And they will be 0 when x is 0 because x to the 1/3, so 0 to the 1/3 is 0 times 3 is 0. So x can now not equal 0. If you wrote that out in interval notation, you have that jump, if you will, at 0. So now I have a new restriction. So when I'm listing what are my critical numbers or critical values, I would want to include x equals 0 as one of those. And don't forget that one, because that one comes from that second part of that definition, which says you need to match their domains and see if there's a new restriction, right? And this x cannot be 0 is a new restriction. Okay, so now I'll take this derivative and set it equal to 0. And again, I think personally for me, one of my favorites is adding the negative term to the other side because then I'm creating a proportion and I can usually solve proportions pretty well. All right, so again, whether you multiply both sides by your common denominator or whether you cross multiply, however you learned to solve this proportion, please do. So maybe it's 3x to the 1/3 equals 6x to the 2/3. You can see that you can divide both sides by 3, hopefully. But what you can't necessarily see is now maybe a clear path to solving. Well, think back to something you know from before. X maybe squared equals x to the fifth. I'm just making up a new problem where exponents are different, one's bigger than the other. So how would you solve that? You cannot divide by variables because you would be getting rid of answers. So instead, we said move one of them to the other side by subtracting it and fact. That's exactly what I'm going to do now. So I take something that I've known for a long time, right, and apply it to something maybe I haven't seen in a long time. So I will come up here and I will say 0 equals 2x to the 2/3 minus x to the 1/3. Now, if factoring is not your cup of tea, and let me show you how this factors, x to the 1/3, right, is my smaller exponent. And then I would have 2, and be careful here, because if you factor out x to the 1/3, you're going to have 2x to the 1/3 left, because when you add your exponents, you get 2/3. And so 0 equals x to the 1/3, and 0 equals 2x to the 1/3 minus 1. This one you're going to think, oh, good, it's x equals 0. But again, anytime you're multiplying by a common denominator, which is basically what that does, you're adding answers that may or may not work. So you probably heard of extraneous solutions in the past. That's exactly what that one is, right? Because if you look back to your f prime unchanged, whether you look here or here, x cannot be 0. And then 1 equals 2x to the 1/3. Divide both sides by 2. And then you're cubing both sides. So if I cube both sides, if I cube 1 over 2, I get 1 over 8. And cube the x to the 1/3, I get x. So I have two critical values for this. I have x equals 1/8. Sorry, I'm very low to the bottom here. And x equals 0. And again, not because when I solved I got x equals 0, but rather because it was a new restriction to my domain. So don't be fooled by some of that solving, right? And you got to make sure you're looking at those domains as well. So if I reflect back on these four, the first two, A and B, did not have any restrictions to the domains, and there were no changes to those domains either. If I look back at C and D, they may or may not have had restrictions when they started, but then once I found the domain, I found at least one additional place where there was a restriction to that domain, and I have to include that number in my critical numbers list. And usually, yes, it might be 0. It just depends on what's underneath your radical. It could be an x minus 1. Well, then it's not going to be x equals 0 anymore. So let's look real quick at two more that are completed for you for multiple reasons. The first one being this E. And so I'll just show you, kind of walk you through it real quick. What this is you have a function cubed. And so you have to use chain rule to find its derivative. Bring down your exponent, keep your base the same, subtract 1 from your exponent, and then times the derivative of what's inside. There's no changes to my domain, right, of the original and to the derivative. So I have no new restrictions. So I set that derivative equal to 0. And I just wanted to point this one out, because if you have to use chain rule in your derivative, it is often the case that you are still in factored form. So then setting it equal to 0 should not be that big of a deal. It should go rather quickly and smoothly, which is what it did there. Pause it if you need more time with that problem, please. And then this last question, F here, we're still finding critical values. I rewrote the problem instead of the square root to be to the 1/2. And then when I found the derivative, again by chain rule, right? I'm going to look at the domain of both. Well, in the original problem, the 9 minus x squared has to be greater than or equal to 0, which I think you can see there up at the top. So if x is bigger than 3, that's not going to be true because let's say x is 4, that would be 9 minus 16, which 9 minus 16 would be a negative number. That is not greater than 0. Or if you look at this graph, it's a parabola that opens down. It has zeros at -3 and 3, and so it looks, well, 9 would be way up here, but it looks something like so. And so it only exists, and excuse me, I need to delete these parts, right? So it's going to look pretty much like a semicircle there, only between -3 and 3, okay? So I can be more precise. Maybe let's see if x is 0, square root of 9, so this would be 3. So this looks like a semicircle, even though mine looks more like an arc. But if I looked at the graph, that's what I would see. So again, I can see the x values only exist between -3 and 3, or on a number line, I drew that as well. So my starting domain for my function is between -3 and 3, can include, because again, that just makes it square root of 0, and I can do that. Once you find the derivative, though, now you have a negative exponent where before you did not. So now that's going to cause trouble. So if you do a rewrite of this, you might see it better because it would be, I can multiply -2x and then divide it by the 2, so I get -x on top and the square root of 9 minus x squared on the bottom. And I did that when I set it equal to 0 right below here, but just wanted to say it with the g prime of x. So maybe now I can see that whatever before made that square root 0, which would be my 3 and my -3, now I cannot include it. So see here, my domain does not include 3 and -3. So I do have new restrictions at x equals plus or minus 3. So these two values need to be in my critical values list. They are not necessarily solutions to my first derivative equaling 0. They are just the second part of that definition of critical values. So then I set my derivative equal to 0, and I chose to go from the fraction with the radical, and I got x equals 0. And x equals 0 is within my domain, so I do have all three as critical values or critical numbers. I hope you found this helpful for critical numbers or critical values. I think the largest problem that we have in some of these is our algebra. So please go ahead and send your instructor any questions you have with how to solve that algebra or how to work through some of these problems. I will make a follow-up video on the absolute max or min as well for 4.1. Thank you.